So welcome back. In last class we have seen that the introduction part of the digital system design through VHDL. So where we have seen that what is digital system design, what are HDLs are available, what is meant by FPGA, what are the different types of FPGAs we are going to use, and uh, of course what is the tool, what is the software tool is used. So those concepts we discussed in the last class. Now coming to this class session is about the transistor as a switch. The transistor as a switch. So in digital circuits, in order to implement various logic circuits, the basic element is, our basic semiconducting device is a transistor. Okay, that too in the transistor's case, the MOSFET is preferable transistor. Okay, and you know the the applications of a transistor are switch and amplification mainly. Out of these two, the is used here. That is, if you observe here the slide, how the transistor working as a switch, so that what is the action of the circuit. So let us see. So the V input is the control voltage on the device to represent whether it is on state or off state. Or at the same time you can treat off state is considered as a open, on state is considered as a short. Suppose if the Vin is, that is input voltage is 0, if the input voltage is 0, the transistor acts as a, this is a switching or transistor switch, this is a transistor switch. Suppose if the input voltage is 0, the transistor action is open switch, that is, or half switch, so that it acts as an open circuit. No current is passed from one end to the another end, hence the output voltage is 0. But if you see the second setup, that is here, since the input voltage is at VCC, therefore the transistor acts as a on switch, that is a closed circuit. It forms a closed circuit between input to one terminal to another terminal, so that the output voltage here is equal to VCC, right? Here since the switch is in closed mode, a current will pass from one end to the another end, so that a voltage will develop across R. Therefore the output voltage is almost equal to the VCC value. So like that the switching characteristics of transistor we can observe here. So this is the technique used in the realization of different types of gates. Let us come to first of all the gate like buffer. Of course is not the gate. So a buffer circuit is there. Okay, it is very helpful in the realization of the digital circuits. We can see in later classes what are the advantages of the buffer. Okay, so this is the symbol usually for the buffer circuit. Okay, and from the previous knowledge you can say that in case of buffer, the output always is equal to the input. Buffer always is equal to the input. But what for this additional circuit buffer we are going to use without any change in the input at the output means the buffer purpose is maintaining the proper matching. Generally called impedance matching. For proper impedance matching, the buffers are used. Okay, let us observe that circuit. Okay, another circuit is of course the previous action whatever we have seen for the transistor switching case, it shows the buffering action. Okay, that is here. In first one case the output is equal to the input, that is 0. In the second one case the output is equal to the input, that is VCC. So if the output is equal to the input, we can observe in case of buffer circuits, and this is a symbol used for the buffer. Then coming to the realization of NOT gate using this switching structure. Let see the circuit arrangement. The switching circuit arrangement is like this. Okay. So suppose here there are two contact points with the switch. Suppose if the input is 0, if the input is 0, assume that the input is 0, assume that the switch contact is at VCC. The switch contact is at VCC, that is like this, so that the output, expected output is equal to VCC. The expected output equal to VCC, since the switch is forms as a closed circuit between terminal 1 and the output. Okay. Similarly, suppose if the Vin is 1, the contact of a switch is between position 2 and the output. So that what is the value at the position 2? That is 0. Okay, that 0 is the expected value at the output. So with reference to this arrangement of logic connection, the output is complement of the input. The output is complement of the input, so that it acts as a, or you can treat it as NOT gate. You can treat it as the NOT gate. Okay. So its functionality you can represent simply as the output is equal to 1 if the input equal to 0, or the output is 0 if the input is 1. Okay. So the circuit which produces complement input is considered as the NOT gates. Okay, are also called inverter. Okay, so and this is a symbol for the NOT gate. Okay, and next one is OR gate. So in OR gate, so what is the switching connection to represent the OR functionality? That is like this. The circuit arrangement is like this. Suppose here in OR gate case, a minimum of 2 inputs we have, Vin1 and Vin2. Suppose Vin is 0, and Vin1 is 0 and Vin2 is 1. Or let us take first both the input values are 0, 0. Both inputs are at 0. Means the circuits acts as a open circuit. The switch in the half mode, so acts as a open circuit, so that no current will pass from one end to the another end. Hence the output also 0. Okay. And suppose if one input is 0 and another input is 1 out of these two, since they are connected in parallel, so if one switch is in closed, means there is a current flow you can observe between one end to the another end, so that the output becomes VCC. The output Vout equal to VCC. Of course, if both are in both the inputs at logic 1, both the switches are 1, acts as a closed, so that case also Vout equal to VCC. Okay, so this structure performs the OR functionality. So what is OR functionality? If any one of the input is 1, the output is 1. Otherwise it is 0. If at least one of the input is high, the output is high. Otherwise it is 0. Okay. So the expression way, that is the action can be represented here like the output is 1 if either input is 1, otherwise it is 0. Okay. Then coming to realization of AND gate. In case of AND gate, here also we have seen two input AND gate, so that two switches are used and their connection is in series mode. Like this between VCC and Vout. Okay. So if and also the AND gate functionality is the output is logic high if both the inputs are at 1, at high, otherwise it is 0. So see the circuit action. Suppose if both the inputs are 0, 0, no switch is in closed mode, So no current pass between one end to the another end, hence the output is 0. Suppose if one input is 0 and another input is 1, here also no current is passed to the one end to the another end because the switches are connected in series. So in order to see the current flow from one end to another end in series connection case, all the switches must be switched on. Okay, so that is happen when both the inputs are at logical high. Both the inputs are at logical high, then the output V out is equal to the VCC. Okay, so that is the circuit, switches connection to show the AND gate functionality. Okay, so like that the different logic gates we can frame using switches, and this is a symbol with reference to the AND gate, and in previous slide we have seen the symbol for the OR gate, and in previous slide we can observe here the symbol for the NOT gate. NOT gate and switching arrangement showing the NOT gate functionality. This is the switch arrangement for showing the OR gate functionality, and this is the switch connection arrangement for showing the AND gate functionality. Okay, so like that the logical gates can be realized using switching connections. And in the next class we can see about the FPGA, what are the different blocks are there in the FPGA, and what is the function of each and every block. Okay, right.